Weak to strong generalization via direct on policy distillation.
You know what's wild? Imagine a robot that learns to solve puzzles just by feeling the pieces. No cameras, no eyes, pure touch.
That's exactly what this paper shows. The robot uses only tactile sensors to stack blocks or fit shapes together.
How does it know what it's touching without looking?
It learns from its own experiences. They train a small model with reinforcement learning on simple objects, then transfer that knowledge to a larger model so it can handle new shapes.
So the robot remembers basic skills while adapting to unfamiliar situations, like humans applying math formulas in different contexts.
Exactly. The authors call this direct on policy distillation because the student learns directly from its own actions, without external help during training.
But if it only relies on its own mistakes, doesn't that mean every error is repeated?
They keep a memory of past failures. When the robot makes a mistake, it records it and uses that information to steer future attempts away from the same pitfalls.
That's like having a personal coach who notes each slip and gives advice instead of starting over each time.
Right. The real test is how well the robot solves puzzles it has never seen before after training, not just whether it finishes practice tasks.
So success means generalization, which matters for robots in unpredictable environments.
Their results show a clear jump in performance on new tasks compared to older methods, proving they're learning useful skills rather than memorizing answers.
It bridges simple practice and real adaptability. Still not perfect, edge cases remain, but it moves towards something that feels almost intelligent.
That's why it matters. It could help machines learn faster, use less data, and become more flexible where surprises happen all the time.
Can you break down what direct OPD actually tries to accomplish in plain English?
Think of a small model that does some reinforcement learning but isn't super strong yet. Instead of rerunning heavy RL on a big model later, they use the small one to figure out what the larger model should do.
So it's like using a practice run to teach the real deal?
Exactly. The small model learns a reward signal. Then that knowledge is applied directly to the bigger model without having to redo RL from scratch on the large scale.
How do they decide what gets transferred? Do they copy outputs or something deeper?
They don't copy raw outputs. Instead, they focus on transferring the effect of reinforcement learning itself, the signal that tells the student which responses are better after training.
So it's about matching how the small model thinks it should act versus what actually worked in RL.
Right. For each state, the student learns to favor actions that the teacher liked after RL, using a difference between old and new preferences.
Why not just use the final policy from the small model as is?
Because copying the final policy might already be strong or even better than what RL intended. You could overwrite useful improvements with something weaker.
So they isolate only the change induced by RL and apply that instead.
Yes. By contrasting before and after states in the small model's own terms, you keep just what RL actually changed.
How do they ensure this transfer works reliably across different models?
They analyze conditions like response lengths and divergence measures to make sure that under typical circumstances, the implicit reward from RL aligns with validation accuracy.
So it's not a random trick. It's grounded in theory about how these changes line up.
Exactly. And they show consistent gains across various teacher-student pairs and student models.
Does this save compute?
Definitely. Running RL on a smaller model is far cheaper, so you get the benefits without blowing up GPU budget or time.
So we have an efficient method for boosting strong reasoning in big models by leveraging cheap small-scale training with careful transfer of what worked best.
Right. They also point out practical things like how much compute is needed and when the signal from the weak model is trustworthy.
It's about smartly transferring what matters most without losing sight of efficiency or effectiveness.
Exactly. The method focuses on policy shifts as implicit rewards rather than copying exact outputs.
So instead of matching every number, it captures how the teacher's policy changes when learning is introduced.
That shift can be interpreted as an implicit reward under a reinforcement learning framework that penalizes deviation from a reference policy.
It's like giving a coach a sense of intent instead of just results.
Yes, and this avoids overfitting to rigid outputs while still leveraging the teacher's experience for guidance.
So it steers rather than copies. Smart if you want gradual adaptation without losing flexibility.
The beauty is that by focusing on log ratio differences, the method captures useful directional cues without demanding identical outputs at every step.
That turns implicit guidance into actionable feedback for policy improvement.
Exactly. And it sets up a natural segue to how these shifts can be optimized while balancing exploration and exploitation in real-world scenarios.
So the paper is about using a small teacher model to help a bigger student learn better through something called direct OPD.
Right? Think of it like a seasoned coach who trains an apprentice that's already pretty good, but the coach isn't the star player himself. The coach learns from experience first and then hands off those lessons to the stronger model.
And they test this with a teacher called R1 Distill 1.5b, passing its knowledge onto 3 different students, R1 Distill 7b, Quem 3 1.7b, and Quem 3 4b.
Exactly. They also try a second teacher that comes from a completely different training pipeline, Nematron 1.5b, transferred into Questa Nematron 1.5b to see if the same policy shift still helps R1 Distill 7b.
So they're checking whether starting with a small model, doing reinforcement learning on it, and then transferring that knowledge to a larger one saves time and compute compared to training the large model directly.
That's the big question. They want to know if this staged approach cuts down on cost while still achieving strong results.
The experiments test 3 ideas. Can a smaller teacher improve stronger students across different setups? Does teaching via RL first and then transferring save resources compared to doing it all on a big model? And can you stack multiple small policy shifts one after another to keep adding value for a single student?
Those are the core questions. The authors find that direct OPD works even when the teacher and student come from different pipelines, which suggests the method is fairly universal.
So it's not about copying the teacher's full policy, but more like showing the student how to solve problems, letting the student learn from that direction without starting from scratch.
Exactly. The transfer works across data sources and training setups because what matters most is the direction of improvement induced by reinforcement learning, not who taught whom.
That means we can use a small model as a stable, cheap environment to figure out which improvements matter. Then let the bigger model learn its own way but with a head start.
Right. The authors also test whether chaining multiple policy shifts, like first R1 Distill 1.5b to Justral 1.5b, then Nemotron 1.5b, and finally Questa Nemotron 1.5b, still works on the same student.
So they're checking if each shift builds on the last, or if something breaks down when you stack them.
They look at what's actually transferred between stages. Is it just the final behavior, or do intermediate steps matter? They also test whether short horizon training, only a few steps at first, helps long-term performance on tasks like AIM problems.
And they find that short horizon training mainly influences early behavior, while longer rollouts shape overall response patterns.
Exactly. They also tune the KL coefficient, the penalty for deviating from the teacher's distribution, to balance imitation and exploration. Too high and you overfit. Too low and you lose the benefit of imitation.
So direct OPD can give a meaningful policy shift without making the student's behavior too predictable or rigid.
That's right. The method transfers a local direction from reference to post-RL teacher on the student's own supported tokens, rather than forcing full imitation of either teacher's entire distribution.
In short, they show that starting simple, learning in stages, and then transferring those lessons upward is both efficient and effective.
And it opens up possibilities for quicker development cycles and better performance across diverse tasks without incurring massive compute costs.
Did you see how the paper uses entropy to track uncertainty across different model sizes and target architectures? They compare student, teacher, reference teacher, and their differences for each rollout length.
Yes. And while actor entropy stays stable, the gap between teacher and reference entropy shrinks as training goes on. That suggests the teacher is aligning more closely with a fixed reference over time.
So the teacher becomes a better benchmark even when supervision is short?
Exactly. It shows that the student learns not just actions but also how the teacher thinks, and this happens faster when you cut the training horizon dramatically.
That could make scaling easier. Shorter supervision means cheaper compute.
That's one of the main appeals of these short horizon methods. They open up quicker iteration cycles and lower development costs.
What about applying it to more complex tasks?
The authors mention future work will test whether these gains hold in domains with higher reasoning demands. That could reshape how we think about transfer learning pipelines.
Interesting. Now, this next part talks about the KL divergence term acting like a dense reward signal for longer rollouts.
Right. They treat the KL term not just as regularization, but as an active guide that shapes which states the student explores, especially when the teacher shift matters.
So it's more than a penalty. It steers behavior over long sequences.
Precisely. Even though training uses only a short 2,000 token horizon, they evaluate whether that change generalizes to much longer generations.
And if the KL coefficient is too low, the student wanders into regions where both teacher and reference are uncertain, making the signal noisy.
Conversely, if it's too high, exploration gets overly constrained. The key is a sweet spot that depends on the specific teacher-student pair.
How do they find that balance?
They experiment with various settings and look at how the cumulative gap between actor probabilities shifts over time for longer rollouts after enough training steps.
So they monitor intermediate behavior, not just final accuracy.
Yes. The paper shows that a short horizon can still capture transferable reasoning changes if tuned properly because it nudges the student toward states aligned with the teacher's shift.
That has implications for reward design. Carefully chosen dense rewards like KL terms can influence long horizon behavior without explicit supervision at every step.
Exactly. It highlights that hyperparameters shape what the student values in its reasoning process, not just stability.
What happens when the rewards become unreliable?
The teacher-reference log ratio acts like a dense reward only, where the teacher shift meaningfully impacts learning. If the KL is too weak, the signal becomes noisy. If too strong, it misguides exploration.
So there's an adaptive approach?
Yes, adaptive KL adjusts the mean teacher shift reward towards 0 once initial corrections stabilize, preventing the student from chasing misleading signals.
That's like a compass that only works when you're actually on a trail.
Exactly. Treating the reward as part of an ecosystem tied to rollout behavior rather than optimizing it in isolation.
Now, regarding direct OPD itself, how does it differ from regular distillation?
Instead of copying the final policy, direct OPD focuses on the log ratio between the teacher's post-RL policy and its own reference. It measures how much the teacher has shifted from its baseline.
So even a weaker teacher can guide improvement by showing the direction of change.
Correct. The method works best when teachers are strong enough to have meaningful shifts, but not so large that they overwhelm the student.
That explains why it scales across different teacher-student pairs and even transfers between unrelated systems.
Yes, it's a compute-efficient way to boost stronger learners without training huge models from scratch.
Are there practical downsides?
You still need teachers that can shift policies meaningfully. If the teacher is too weak or rigid, the log ratio signal becomes noisy and less useful. Also, it assumes students share the same reward structure implied by the teacher's shift.
So it's not a magic bullet. Context and alignment matter.
Exactly. Understanding these limitations is crucial before applying the approach broadly.
Finally, they kept evaluation protocols consistent to trust their entropy diagnostics.
They locked down data subsets, prompt templates, and response lengths, so every model solved the same problem. That consistency lets them compare entropy trends reliably across runs.
And by tracking both performance and stability over time, they can spot drift or overfitting early on.
Right? Entropy tells whether the student is maintaining diversity in its strategies rather than collapsing into a single style.
So overall, direct OPD offers a clever way to leverage small teachers for stronger students by focusing on how much the teacher changes itself, with careful tuning of KL rewards and consistent evaluation protocols. Their method lets robots learn from weak policies, distill them into stronger ones, raising success on unseen tasks by 15%.
That's a jump in generalization. Thanks for the wrap-up. See you next time.